Welcome! With this video, we begin Math 110, the fundamentals of mathematics. This course is broken into three parts. Part 1 is making sense of reasoning. Part 2, making sense of numbers. And Part 3, making sense of operations. With these basic ideas, we get the fundamentals of mathematics. So let's begin with Part 1, making sense of reasoning. Now, this part has two chapters to it, logic and sets. In logic, the first topic we cover is statements and conditionals. So let's begin that. Chapter 1a, statements and conditionals. A statement is a claim that is either true or false. Which of these are statements? Take a look at these and see for yourself. All right, what do you think? How about number 1? 2 plus 2 equals 4. Yes, that is a statement. How about number 2? 2 plus 2 equals 5. That is a statement. It is not a true statement. It is false, but it doesn't have to be true to be a statement. It's just simply a claim that is either true or false. How about number 3? John F. Kennedy was a great president. Well, that's really more a matter of opinion. I suppose you could establish officially what a great president means. You could define that, and then you could judge him against some criteria. But generally speaking, no, this is not a statement. Number 4, I like that exclamation, but no, that is not a statement either. Number 5, tomorrow I will win the lottery. What do you think? This one's a little tricky. This is a statement, but we don't know if it's true or false. Now, it is definitely true or false, because definitely, tomorrow I will either win the lottery or I will not win the lottery. So it is a statement that's true or false, but curiously, we actually just don't know whether it's true or false. Now, a compound statement combines statements with and, or, unless, then, etc. So for example, you could say, tomorrow I will win the lottery and 2 plus 2 equals 4. Yeah, that's one thing you could say. Or 8 is an even number, or elephants have trunks. One particularly interesting way of combining two statements is what's called a conditional statement. So a conditional statement has the form if A, then B. So where A is a statement and B is a statement. So for example, if it rains, then I get wet. If n is a multiple of 4, then n is even. It connects these two statements together. We would write this as A with an arrow B, and sometimes you see just an arrow that has like the single line like that. And we read this as A implies B. So if A, then B, or if A is true, then B is true, or A implies B. All these kind of ways of saying it. Let's take a look at these three statements and just rewrite them as conditional statements. So how about number 1? I go inside whenever it rains. How would you write that as if then? I go inside whenever it rains. So, in other words, if it's raining, that will cause me to go inside. So, if it rains, then I go inside. All right, so there it is as an if then. How about statement number 2? I will play soccer if it's sunny. Well, we actually do this a lot in the English language. The if part of the statement is at the end, and the conclusion is actually at the beginning. We switch them around, but that's okay. It's common language. We know what that means. But if I'm to write this formally, I might say, if it's sunny, then I will play soccer. And statement number 3, every multiple of 10 is an even number. How about that one? We got every multiple of 10 is an even number. So that means if I'm looking at a number that is a multiple of 10, then it's an even number. So how about if some number is a multiple of 10, then it is an even number. Or you could put a variable in there to make it flow a little bit more easily, perhaps. Say if x is a multiple of 10, then x is an even number. I'll just say x is even. There we go. So a lot of times we say statements that can be translated into if-then statements, and these are conditional statements. I can negate a statement by putting a little tilde in front of it. So tilde A means not A, so it's the negation of statement A. So if A is the statement, it is raining, then not A is the statement, what do you think? It is not raining. Now, with conditional statements, there are various ways that I can order the two different statements and their negations. So perhaps my original statement is the form A implies B. If I switch the order of B and A, I get what's called the converse of the statement. The converse is B implies A, just switching the two orders around, just switching the two statements around. The inverse of the original statement is not A implies not B, and the contrapositive of the original statement is not B implies not A. So let's see how this works with an actual statement. Let's apply it to the statement, if it is raining, then there are clouds above. So it is raining, that's my statement A, and there are clouds above, that's my statement B. So the original statement, A implies B. If it is raining, then there are clouds above. What is the converse of that statement? If there are clouds above, then it is raining. How about the inverse? Not A implies not B. If it is not raining, then there are no clouds above. And the contrapositive? If there are no clouds above, then it is not raining. If a statement is true, will its converse also be true? What do you think? Well, take a look at the example above. The original statement was, if it's raining, then there are clouds above. Well, let's just think, in our real life experience, is that true or false? And that's true. The only time you see rain is when there are clouds above. So I'll just label that T. That really is a true statement. But what about the converse? Is that true? If there are clouds above, then it's raining. No, our real life experience tells us that's not true. Plenty of times there are clouds above and it's not raining. So that's actually a false statement. So considering our question below, if a statement is true, will its converse also be true? That's not always the case. It's certainly possible that a statement can be true and its converse can be not true. I sometimes think when people get into arguments, they run into a little bit of a logical fallacy of mixing up statements and then their converses. Now, it turns out that among these four ways of seeing an implication, two of these are equivalent statements. There's the original, A implies B, and it turns out A implies B is equivalent. It's the same thing as not B implies not A, the contrapositive. So let me highlight those. The original and the contrapositive, those are equivalent statements. If the original is true, then the contrapositive is true. If the original is false, then the contrapositive is false. Whatever one is, the other is as well. And kind of see this. Is the contrapositive true? Let's read it out loud. If there are no clouds above, then it is not raining. Oh yeah, that's true. And is that really equivalent to the original? The original says, if it's raining, then there are clouds. So what do I know? If there are no clouds above, well, then according to my original statement, there can't be any rain, right? It can't be raining. So whenever the original is true, then the contrapositive is true. Also, the converse, B implies A, the converse is equivalent. Now I'll just underline that with a squiggle. The converse is equivalent to the inverse. The inverse, not A, implies not B. And not to confuse matters too much, but look at what's going on here. This relationship between the converse and the inverse, well, that inverse is the contrapositive of the converse. What have I done to get from the top line to the bottom? I've switched the order of the two statements and negated them. So the contrapositive of the converse is the inverse. The last idea I want to talk about is if and only if statements, the biconditional. A, if and only if B. And sometimes you see the little notation IFF. What this means is that there is an implication in both directions. If A is true, then B is true, and if B is true, then A is true. Here are a couple examples of if and only if statements. A number is even if and only if it ends in 0, 2, 4, 6, or 8. Let's see if that's true really in both directions. So if a number is even, then it ends in 0, 2, 4, 6, or 8. Well, that's true. That's kind of what we know about even numbers. Well, how about the other direction? What if I start off with a number that ends in 0, 2, 4, 6, or 8? If that's true, then moving to the left, it means the number must be even. So it's true in both directions. How about the second example? A triangle is isosceles if and only if it has two sides of equal length. So recall an isosceles triangle might look something like that. And so if it's isosceles, then it has two sides of equal length. So that's true. And if it has two sides of equal length, then it is isosceles. So the implication in the other direction is true as well. So there it is. We've covered statements, conditionals, even the biconditional, and that gives us a good start and covers section 1A.